we now know that there are many ways that we can manipulate information in the neural network. Actually, what I would like to emphasize today will be about the types of the output that you will get versus the task that you may want it to be used it for. Like, for example, if you want to use neural network for regression, right? And you have the input of size, maybe Rn, like that. And you fed that into a neural network, let's say denoted as a G function. If you get a single scalar value, that is a float value, then probably it's a regression task. But in fact, you can get more than, let's say, more than single scalar like this. You can get like a vector. Let's say if your function is mapping from Rn to R, let's say Rc times n, then you get like a vector of, let's say, regression value. That can happen as well. If you want to, you can reshape neural network to provide such output. Another task that neural network can provide is a classification. Another type of output that neural network can provide is classification. For example, if all you want is a value between 0 or 1, then maybe you provide it like an input, and then your neural network will give you the output that is a value between 0 and 1, or binary value, if you want to do binary classification. But if you want to extend neural network for multi-class classification, then this is actually the one that we will focus on in this lecture. That is because, let's say, in binary class, it's just 0 and 1. And actually, if your classifier provide like incorrect result, let's say if the class supposed to be 0, but the classifier give you a class 1, or vice versa, the error distance between 0 or 1 is just 1. But if you have multi-class, let's say class from 1 up until 5, what if you incorrectly forecast class 4 to class 1 versus class 4 to class 2? Which incorrect classification is worse? Actually, it shouldn't be which one is worse, but they should equally be incorrect. So that's why mapping classes to integer value like 0, 1 to 5, something like this, is not something that people would do. It is because when you use the output class and use that to measure the error that you get could be very much like incorrectly interpreted. That's why later on people try to come up with a representation of a binary vector again, but this time they use like what we call a one-hot vector. Actually, it should be 1 like that. One-hot vector is a vector that has only single coefficient as value 1, and the rest of that has value 0. But we can use it to represent a class where, for example, if we say that the output of this classifier should be in class 2, right? We could use, let's say, if we know that there are 5 classes, maybe we can use, maybe 4, in this example is 4 classes. Maybe we use a vector that has a coefficient at location 2 to represent class 2 for all 4 classes. Something like that. So this binary vector is good for the fact that, let's say, if the class that you want to predict is class 2, and accidentally your classifier give you class 1, so it gives you this result. The difference between this vector and this vector is like when you do, okay, let's negate. It will be 1, maybe you can do XOR, exclusive OR. If you do exclusive OR, then that will be maybe, not sure. Okay, it's only like around this, right? Yeah. Something like this? Right. But what if you have predicted as class 4 instead of class 2? It will be like this, right? So it will be, oh, sorry. So somehow if you sum them together, this is like a distance of 2, this is like a distance of 2. So somehow the difference between, like, the difference that is caused by the errors of your classification wouldn't be that different compared to if you were to use integer to represent them. So that's the reason why people sometimes prefer using this one hot vector over. Okay, let's go to one more extreme case and then we will go over the learning loss function, and that's it for this lecture. Okay, another extreme example is when we have to consider multi-label and multi-class. And actually I should point out the fact that multi-label simply means that you are trying to identify more than one class on the object. That is like multi-label. For example, if we take a picture of this scene, right? And we ask the computer to identify whether or not the scenes that we took picture of has human. So this is like just one class. But if we ask how many objects and what types of objects are there, then this could become like a multi-label and multi-class. And in this example, maybe to make it clearer, maybe you take a picture of a man and you want to classify the accessories that the man has. Maybe you will use multi-labels, and that means that you are considering the labels on the head, the face, the body, and the feet. Right? So that means you have 4 labels to consider. But for each label, you may have different number of classes. For example, on the head, maybe you are considering only whether or not the person is wearing something on the head, like is he wearing a hat or a beanie, or none. For the second label, maybe you're considering whether or not a person is wearing a glass, and that's it. So one label may be having different number of classes. But the thing is, if you would just use like a vector of integer, you can pretty much represent all of these cases like in a very neat way, because you can just allocate the number. But as we know that if we use integer like that, there are problems with the, like the distance, the error distance, that, the error between 1 and 4 may not be, maybe, it is like, it's suggesting that 1 to 4 is large and 1 to 3 is small. But then you want they to have the same weights for the errors because it's misclassifying. Stuff like that. That's the reason why you rather have it as a binary. But when you put them as the binary, you have to make sure that the dimension of your binary vector, or maybe matrix now, is somewhat consistent for all of your labels. For example, at the moment, the maximum number of classes is 4. So that's kind of reason why you would have a matrix of 4 rows times 4 columns. For the rows, it's like the number of labels that you have, but 4 columns is because of the number of classes. That is like the maximum is 4. So this is kind of like the reason. But yeah, problem like this is like, how should I say, it could be challenging when you construct a neural network, because you have to make sure which layers of your neural network will represent each of these labels, and how you get, or how would you concatenate the output so that you could concisely represent all of them. That's like a systematic challenge. But right now we wouldn't care about this. We would just consider this case where you want to do like a multi-class classification. Because in fact, if we think about multi-class classification, it's like extension from the binary class classification. Previously, we've learned that in binary class classification, we use something like a binary entropy loss, which deal with the probability, because we say that we don't want to use regression because regression is like, we don't want to use MAE because the absolute error could be like a distance between 0 and 1, but we prefer something that is more precise and have the meaning tied to the fact that representing a class or not. But when we do multi-class classification, as we can see, we can use binary vector. So that means that whatever we have in here, we can extend it to here. Or if we start from multi-class, we can always go back to what it would look like in a binary classification as well, in terms of the loss function. Okay. So that will be our main target today. So let's say if we have a training set where we have the measurements to represent the label in the training sets up until m samples, and we have x to be our inputs. Let's say if we have 1,000 samples, so that m is equal to 1,000. And let's say if we use beta to denote the set of model parameters in deep learning, we can formulate the learning loss using maximum likelihood, just like this, where y is representing the class that we want to infer and x representing the input, because in this likelihood we are considering the joint relationship between all the samples. Then we can actually provide that into like a joint distribution between all m samples. After that, when we have these m samples, we can use the assumption that each of these samples are independent. And instead of writing this as a joint function, we will provide them as a product between each samples. Like that. Okay, I'll put this way. And because then we may want to consider this probability of, let's say, of forecasting that class equal to, let's say, a Q class given xj. Xj is just an input sample, where Q is denoting, let's say, the integer value representing the class. Let's say you have up until class C. I think this step still somewhat what we know. Like if it's just binary, it will be the set of Q will be just 0 and 1. right? And then from this products of probability, we may convert that into a log scale, where we take the log, then that becomes sum of the log. And sum of the log could be like our new function for the loss function. And we do this because we want to avoid it over underflow problem. That's where we produce many value that's between 0 and 1, then very likely we're going to have a 0 value. So we do this instead. Then this is a part where we start to reshape our problem from where if we have, like if we were to consider Q as integer value and we want to map it into, let's say, a binary vector. And in this case, let's say we use one hot vector where, let's say if we say that Q is a class 2, maybe we can use like a vector of maybe all 0 except the location 2 that is equal to 1. Something like this. There are many vectors like that could represent this class. But just to denote that sometimes we can use a set denotion as 0, 1, and to the power of c, just to refer to the fact that the size of this vector could be like c times 1. Okay. Then after that, because we know that the probability of maybe our measurement being like a class Q, maybe Q is equal to 2, we can represent it with the one hot vector. Then we may be decomposing this into probability of that coefficient at the second location equal to 1 and the rest equal to 0. So that is like the way that we may decompose it. After that, we take the logarithm. Then you can see that we can, like kind of differentiate this term out of the rest. And the rest of that, let's just go here. And that is like for other coefficient that will have value equal to 0. After that, we may plug them in. So that becomes our loss function for multi-class classification. But what does that mean when we combine that to the system of machine learning or deep learning? That means that we have input vector x, and we fed them into this neural network. Then we get the output vector that is like a one hot binary vector. Let's say if each coefficient of it is represented with C0, C1 up until CC, then that is like a binary vector here. Right? So that means that if we are using this C1, C0, C1, C2, or maybe up until CC, and we want them to, as we recall from previous slides where we used like sigmoid function, that means that if we were to replace this output maybe with the sigmoid layer, we can then map this value into like a probability. And then with this probability, we can actually use that probability to compute the probability in your loss function. Is there anything that is okay? Is it still okay?
We need some time to look back at the video.
Okay, so okay, maybe what I should have said to make it simpler is that, okay, if we have f here as our neural network, we can use whatever activation function for our output. But let's say if we use sigmoid function as our output layers, then that means we're able to map whatever given as an input to a value between 0 and 1 at the output. And this value between 0 and 1, it can use to represent the probability. And simply is like a probability of being class 1, class 2, or maybe class C. And that could be corresponding to like a binary vector 0, 1, 0, 0. If let's say if this image or maybe input vector belong to class 2, then that means that if we use binary vector represented, maybe only the second location should be 1 and the rest is 0. So that means that, well, pretty much this output is representing the probability. We can actually kind of use it as a pseudo for the probability for being in each class. So somehow, if we do this way, it will enforce deep learning to provide the probability of each class. Then the question is, how can I know that that deep learning is providing us the correct class? Let's say if this one is 1 and the rest of that is 0, if this is correct, it's kind of look correct. But what if our machine learning compute the probability just like this with sigmoid function, but instead provide maybe the first location as 1 and the rest of that as 0? What would happen if we plug that in? What would happen is that if this is 1 and it's kind of like falling into this group, whatever value here will force it to have extremely low value such that it will no longer maximize this, and it will try to find like a new weight parameters to switch from that into that instead. Okay, let's go into detail of what that look like. Okay, first of all, let's think about what that means when we say that, let's say I'll put this way, if Q is the second location, maybe this location, so CQ will be 1 and the rest of that will be 0. And if we were to decompose this probability of C whatever places being 0, then you can rewrite it as 1 negate whatever that output being 1. Yep. So that means, okay, if I will put this way, if this is 2, suppose that the correct class is class 2. If I put this way, okay, this will be log of maybe value close to 1, and the less versus log of value close to 0. And what happened is that what we want is to maximize, right? So you have log 1 plus the sum of log 1. That's equal to 0. You'll do maximizing. But if you switch, let's say, if we know that if our predictor or maybe our classifier giving us the output like this, where it's misclassified, then what happens is that this will be equal to 0, and one of these will make the term equal to 0 and the rest is equal to 1. The thing is, log of 0 will be negative infinity. So that means, okay, maybe I'll put this way. If you misclassify, so that will go minus infinity, that will go minus infinity. So that means that if anything wrong, it will turn this loss function to minus infinity. It will no longer be like a maximum value. And if we think about this is kind of look like the binary cross entropy that we've learned before. That is this function. That is, if we get the correct class, okay, if y is equal to 1 and you predict as 1, but this is a loss, so it's negate and everything, yeah. Then this goes 0. But if you incorrectly provide that, then that would be negate of log 0. Is the infinity. Yep. So that's what it's like when the classifier misclassified, and it will switch the loss to be maybe either very high or very low. That is opposite to the direction of the minimization or maximization operation. Yep. Pretty much that's it for today. Actually, I would like to point out a little bit that is this loss function, I kind of missed this term. What I miss is that I missed the place where P is not equal to Q. It's similar to when I wrote it here in these slides. Yeah. Actually, that's all. Just a little bit before I go. Aside from sigmoid function, there's another layer, that's what we call softmax layer, that can somewhat be used to compute the probability as well. It is like, for example, if you have like a z value that is high and you divide by like sum of the exponential of all, it's kind of look like a probability in a way. Yeah, that's the reason why they sometimes use this one as well, but it depends on what you see as most suitable. Okay, that's all.